So last time we got a little bit into limits involving trigonometric functions. We got to do a couple of limits. One of them was a very straightforward limit. We plugged in the value, we did the direct substitution, and we got a nice value. But for the other one, we had to go through, through a graphing approach, because we got that case in which we had a number over zero, which is not an indeterminate form. Recall that the indeterminate forms for now are 0 over 0 or plus or minus infinity over infinity. Later in the semester, chapter 4 I believe it's going to be, or chapter 5, we're going to go through the L'Hopital's rule, and we're going to look at other indeterminate forms. So you will see about it later. Okay. So in order to move on through the calculus of trigonometric functions, we need to talk about a couple of special limits. So the limit of sine x over x, it's a special limit that is equal to 1. And another special limit is 1 minus cosine of x over x equals to 0. Well, in this case, don't even try to do direct substitution, because if you do, well, sine of 0, what's sine of 0 again? Sine of 0, and what? And 0 over 0. Well, this is good. It's a 0 over 0 indeterminate form. However, if you observe that limit, sine x over x, well, there's nothing we can do about it algebraically. Like finding, like factoring, like simplifying a complex fraction or rationalizing. So there's simply no way to get this limit done. However, we will learn about how to get that limit when we get to the L'Hopital's rule later in the semester. In the meantime, we're just going to use these two results to, number one, to compute other limits, and to later find the derivation of a limit, of a derivative formula actually. Well, the thing here is, when we use this limit, these x have to be the same. And over here, these x have to be the same. Well, this is not just limited to x. We can have something else like 5x, 7x, or your favorite multiple of x. The thing is that these two have to match. Like in the first example, we have the limit of sine of 5x divided by 7x. Well, if we observe these two quantities here, 5x and 7x, these two quantities do not match. So the first thing I'll do is take that 7 outside, and find a way to make these two quantities match. So what's missing here in the denominator to match the quantity inside of the parentheses of the trigonometric function? So we can put a 5 in there, can't we? We can multiply by 5 in the denominator, provided we actually do so in the numerator. So we can multiply and divide by 5. That is, like, multiply by special version of 1. So in this case, recall that there are many ways to write the number 1. 1 is equal to 5 over 5, 7 over 7, 1,000 over 1,000. But we're going to choose 1 in particular that make us, or that it's actually useful to have these two quantities to be the same. Well, what am I going to do? I'm going to put these two together. Limit, well, actually let me leave a space in here. Limit sine x, or rather sine 5x over 5x, and that remaining 5 right here, I'm going to have it outside multiplying with the limit. Well, as x approaches 0 in this case, we know that from the definition before, we know this equals to 1. Okay, so that'll be 5/7 times 1, which is simply 5/7. All right. Let's look at the next example. Letter B, secant x minus 1 over x as x approaches 0. Of course, well, if we do direct substitution, well, we should do, okay, let's do one step at a time. Secant of 0 minus 1 over 0. But secant of 0, well, At first glance, it's not easy to just come up with the value for a secant function. However, we can use trigonometric identities and make this calculation a lot easier. So let's recall that secant then is the reciprocal of cosine. And what's cosine of 0? So this is going to be 1. So 1 over 1 equals to 1 minus 1. And in this case, this is 1 over 1. 1 minus 1. And this is 0 over 0, which is good. This means that we can do something about it. Well, in this case, somehow we're going to turn this limit and make it look like 1 minus cosine x over x to eventually get a limit equal to 0. So let's go ahead and do that. So again, this limit of secant, instead of secant, I'm going to write 1 over cosine minus 1. But how about we write this 1 as 1 over 1, and that to combine fractions together, and the whole thing divided by x as x approaches 0. Well, I left some space over here, and that space I left is to find a common denominator, because we cannot combine these two fractions together if they don't have the same denominator. Well, in this case, the missing factor to obtain the least common denominator, or to write a couple of fractions with a common denominator, would be obtained by multiplying by cosine in the numerator and denominator of that second term. So this will lead us to limit of 1 minus cosine x over x cosine x as x approaches 0. Alright, so somehow we see the 1 minus cosine over x, which is that special limit, but we have this cosine multiplying with the x. Yes?
Would this still all be over x, or did we get rid of it?
Yes. Oh, hold on. Okay, no, never mind. Well, that's going to be over x first. And then, oh yeah, that was going to be my next step. Alright? So, yeah, I think I just skipped this step. So in this case, well, that's a limit of 1 minus cosine x over x cosine x as x approaches 0. Well, so that limit, 1 minus cosine x over x times cosine x, already resembles that special limit in here, which is this. But here we have that extra factor of x. So in this case, how about we use properties of limits in order to, in a way, split this into two limits? Because, well, do we agree that this is the same as saying limit 1 minus cosine x over x times 1 over cosine x? Are you guys following me here? All right. So how about we do limit? So we have the limit of a product. Remember those properties of limits? So whenever we have the limit of a product, we can write this as the product of two limits. Alright, so, well, what's this special limit equal to? Isn't that special limit equal to 0? So we can already compute the limit. So that's going to be 0. And well, 1 over cosine of, oh, that's supposed to be 0, not 1. So 0. What's cosine of 0? Isn't it again 1? So this limit will go to 1. So 0 times 1, 0. So the idea here is to manipulate the expression, the limit expression, so that we get somehow to those special limits. Alright? So now let's get into the derivatives of trigonometric functions. Well, So let's talk about the derivative of the function f of x equals sine x. Well, if we were to use the limit definition, we would have to evaluate the function at x plus h minus subtract the original function and divide by h, and well, make that limit approach h equals to 0. Well, so in this case, what do we do to compute this limit? Well, unfortunately, we cannot factor out anything just the way it is. We cannot do something like what's it called, the conjugate or partial, or complex fraction. So in this case, we're going to use a trigonometric identity, the addition of angle identity for sine. Sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So we will replace this identity over here. So that's f prime of x, limit of sine x plus h. So in this case, that's sine x cosine h plus cosine x sine h. So that's going to be minus sine x. All right, so that's minus sine x, and then the whole thing divided by h as h approaches 0. Well, so somehow in this case we need to split this into a couple of limits, and then we will use those special limits from before. And I think we can put these two together, sine x cosine h minus sine. All right, so let me just reorder. So that's going to be sine x cosine h. I'm going to put this minus sign together with the first term, and then plus cosine x sine h and over h. So what do we have in here? We can factor out sine. We can factor it out. Factor out, and oops. That's the limit of sine x multiplying cosine h minus 1.
Wait, I thought you could just cancel them out because then it's a positive sign over x and then subtract the sign of x.
Which one?
0.
To cancel these two? But this is being multiplied with cosine, so we cannot just cancel. So we factor this and then plus cosine x sine h as h approaches 0. Well, what do we have here? We have a fraction with two terms in the numerator. That's one term, that's the second term. Let's split this into a couple of terms. So, or a couple of limits. So that's the limit of sine x as h approaches 0 times cosine h minus 1 over h plus limit of cosine x times sine h over h as h approaches 0. Well, let's have a look at each limit individually. Alright, so do you see this special limit sort of right here, cosine h minus 1 over h? Actually, that looks like this limit, but in a way it's reversed. But in this case, it's not going to matter because you could have written this limit right here as a limit x approaches 0 of cosine x minus 1 as well. And would it make a difference for the order in this case? The reason is no, because the limit ultimately is 0, so it doesn't matter the way you see this limit. So this is what's going to happen here. So this This will make that special limit to go to 0. 0 times sine, what's that going to be? 0. And do you notice something special about this? Oops. What's sine h over h? Isn't that a special limit? And if so, what's that? Isn't that equal to 1? So what is 1 times cosine? Just cosine. And this is how we show that the derivative of sine equals cosine. Do we have to do this for every single formula? No, we don't have to. So let's see. Let's find a formula to find the derivative of the tangent function. Well, so but in this case we're not going to use the limit definition. Question?
Can we about question? Won't you include the x equals x approaching 0 and cos x?
Which one? This limit? I mean the one in red?
At the end, on the right.
This one?
Yeah. Won't you include the 0 value in cos x?
Oh, not in this case because we're evaluating the limit for h, not for x. So everything else is just it remains the same, remains constant in this case. All right. Okay, find the derivative for the function tangent of x. Well, so instead of using the limit definition, how about, well, f of x equals tangent x, and well, we can actually write tangent using trigonometric identities as the quotient between sine and cosine x. Well, what do we need to find a formula for the derivative of tangent? Well, we need the sum of the derivatives that we got. Well, actually, this is not supposed special limit. These are just the derivatives. So this is the summary of the 6 derivatives, the derivatives of sine of all the trigonometric functions. So number 1, as a pattern that you might want to consider here is that the derivatives that start with a like cosine, cotangent, and cosecant, they are all negative quantities. Everything else like sine, tangent, and secant, the ones that do not have a co in it, they are positive in this case. All right. Well, so in this case, the derivative of sine is cosine. The derivative of cosine is negative sine. All right, and so on and so forth. So we're going to use these pieces of information to come up with a derivative for tangent, and we should get this secant squared. How are we going to do this? Well, we have a quotient of 2 quantities in this case, of 2 functions. So we're going to use the quotient rule, which is what we did last time. Let me write down the formula for the quotient rule. So the quotient rule states that whenever we have a quotient u over v prime, that's u prime v minus v prime u. And then the whole thing divided by the denominator squared. Alright? So that's going to be then f prime. Okay. The derivative of u, which is the derivative of sine, that's cosine, times v, which is actually cosine. Actually, let's label this. Let's label this is our u and this is our v. And then minus, in accordance with the quotient rule, v prime, so the derivative of cosine, which in this case is negative sine, times u, which is sine. The whole thing divided by the denominator square, which in this case the denominator is the cosine function, isn't it? Cosine x quantity squared. Alright, let's do one thing at a time. So cosine times cosine, that's going to give us cosine squared. And then negative times a negative, positive, sine times sine. This is going to be cosine squared x. And well, let's simplify this. What do we know about the numerator? What's cosine squared plus sine squared equal to? Isn't that an identity? And that equals to 1. This will leave us with the following result. F prime of x equals 1 over cosine squared of x. But well, that doesn't look like secant squared. Not yet, because we can use the fact that secant is the reciprocal of cosine, isn't it? So secant squared x is the result to differentiate tangent x. Alright, let's flip the page, stop some derivations. Let's actually go through some examples. Okay, so let's find the derivative of the following functions. And in this case, we have a product. G of t equals to t squared cotangent of t. Well, number one, because we have a product of the functions, how about we use the product rule? So then the product rule will state that uv prime, that's u prime v plus v prime u, right? So in this case, the derivative of the first factor times the second plus the derivative of the second factor times the first one. All right? So let's see. Number one, again, I would list everything, you know, like what's u, like what's v, and in this case u would be t squared and v equals cotangent of t. All right, so what's u prime? What's the derivative of t squared? 2t. And what's the derivative of cotangent? Well, let's go back to the table here. The derivative of cotangent is negative cosecant squared. All right, so that's v prime. So let's put everything together in accordance with the product rule. So in this case, g prime of t will be u prime, which is 2t, times v, and plus v prime, which is negative cotangent squared t, and that times u. Okay, let me just label everything just so you can relate to what we're doing. So that's u prime v, and this is v prime u. Just to check with the product rule. Question? Which one? Oh, negative cosecant. That's true. Yes, yes. I don't know where did I get that cotangent. Yes, thank you. Negative cosecant. And let me paint this in. Thank you. So, well, over here there's really nothing to simplify. Actually, just clear the parentheses and just 2t cotangent of t minus cosecant squared of t times t squared. Final answer. That's fine. No need to further factor a power of t, even though it's possible to factor one power of t, but that's fine. Let's do letter B. Notice for letter B, well, what do we have? In the first place, any ideas of which differentiation rule to use on letter B? Quotient rule, and that's because we have a quotient between two functions. And let's write it down. U over v prime, that's u prime v minus v prime u, the whole thing divided by v squared, the denominator squared. So, number one, let's do one thing at a time. So, u equals to secant, and v equals to 1 plus tangent. Alright, what's the derivative of secant? Okay, let's go back to the table above. The derivative of secant, that's the product between secant and tangent. So that's u prime. And the derivative of v. Okay, what's the derivative of 1 in the first place? And the derivative of tangent? Secant squared. So we have everything we need. Let's just put it in the quotient rule above. So, let's see. F prime, F prime of x will be the u prime, which is secant tangent times v, which is 1 plus tangent, minus v prime, which is secant squared, times u, which is secant. The whole thing divided by the denominator squared, which in this case is 1 plus tangent x quantity squared. Alright, let's see if we have anything interesting to factor out. Maybe, well, all we have here is secants, right? And over here we have 1 power of secant, so there's really not that much. So let's just factor secant. That's going to give us tangent x times 1 plus tangent and minus secant squared. Well, there's actually going to be some cool stuff to simplify here, you'll see. Well, so that's 1 over 1 plus tangent x quantity squared, and if we distribute this over here, tangent times 1 and tangent times tangent, that's going to give us the following: secant x times tangent x plus tangent squared minus secant squared x over 1 plus tangent. Alright, this is not the most common trigonometric identity that we use, and in fact we will be able to simplify tangent squared minus secant squared, and we do that by, okay, let me do some work on the side. We do that using this identity here, tangent x squared x plus 1 equals secant squared x. So that's one of the other Pythagorean identities, you know, the one for like sine squared plus cosine squared equals 1. Well, so this is another identity that falls into that category, the one for that are the Pythagorean identities. I'll show you a trick to obtain these formulas in a second. Well, so what happens if we solve for, if we manipulate this identity? So I'm going to subtract secant squared on both sides, tangent squared x minus secant squared x plus 1 equals to 0, and then tangent squared x minus secant squared x equals to negative 1. So this whole thing will be a negative 1. Alright?
Examiner, you're going to be having the rule values if you scroll up on the green,
Like this, you know?
Like what quotient or whatever rule are we going to have?
Oh, these ones, the differentiation, most likely you'll have to memorize them. Yeah. Question?
You have to memorize cosine squared plus sine squared is equal to 1.
Like the basic identities? Yeah. That's those you need to memorize. Like this one, I'll show you a trick to come up with this identity, because that's an identity number 1. We don't use that very often, and if for some reason we need it and we're not provided it on the exam, okay, let me just finish this and I'll show you the trick. Okay, so this is secant x tangent x minus 1 over 1 plus tangent x quantity squared, and this is the simplest we can go about the derivative of this function. Now the trick to obtain these identities. Well, so okay, let me make some space in here first. Alright, so I guess this identity sine squared plus cosine squared, let me do S and C for short. That one is easy to remember. That one we use it all the time because for many reasons. We use it to prove any basic identities, and that's also related to the unit circle where the x is the cosine, the y is the sine. I think it's one. This identity we can memorize it, right? Are we good with memorizing this identity?
Yes.
Okay. So So what if we divide both sides by cosine squared? Well, what is sine over cosine? Tangent. Cosine over cosine is 1. What's 1 over cosine? Alright?
But how do you know that's what it equals? That's what how are you getting at?
Huh?
How do you know 1 over c squared is secant?
Those are the basic reciprocal identities, and what else? The quotient identities. Sine over cosine is tangent, and cosine over sine is cotangent. And then on the other hand, to derive the other identity, same, sine squared plus cosine squared equals to 1. What if we divide by sine squared? 1. That's cosine over sine, which is cotangent. And what's 1 over sine? So that's one way to derive these other two identities that are not, we don't use these identities very often, but what if you get into a surprise, you need them, well, you don't have a formula sheet, you don't have access to internet, for example, on the exam or anything, and you need to use these identities, well, use this as a starting point and derive them from them. Alright? Let's do one more. Y equals to sine theta plus cosine theta divided by cosine theta. Any ideas on how to differentiate this function? What differentiation rule would be okay? Quotient rule? Well, in this case, how about just, yes, quotient rule, it's not a bad idea. It's not incorrect, but this is sine over cosine plus cosine over cosine. Well, this is what's sine over cosine?
1.
Tangent.
Oh,
And cosine over cosine?
that's 1.
Well, what's the derivative of tangent? Isn't that secant squared? And what's the derivative of 1? 0. We're done. So in some cases, no need to go through the quotient rule. In the previous case, we did the quotient rule, and check this out. That's because, unlike letter C, we were able to split the fraction into two fractions. However, that's not possible with letter B. In this case, we cannot do secant over 1 and plus tangent over, or secant over tangent, right? We cannot split the fraction in this case. So we have to do the quotient rule, but this one, no need to get too overwhelmed with the quotient. Alright, so this finishes section 3.3 on differentiating trigonometric functions. So let's go to the next section. And the next section is, where is it? The chain rule. Section 3.4. Alright. Number 1, what about chain rules? So far we have differentiated, well, polynomials or additions of functions, differences of functions, products using the product rule, and quotients of functions using the quotient rule. Alright, so now we also apply that to new functions, which is the derivative of trigonometric functions. However, there's other more elaborate functions that also have to have a derivative, and in this case is the composition functions, and you might remember those from pre-calculus. You might remember this bubble symbol F bubble G, which means F composite G or F composition G, which is some function evaluated not at a value, but rather at another function. So we're going to look at some functions, and we are going to identify what are the two functions that compose together and give that function, like in this case, the square root of x squared plus 1, e to the x squared plus 3x, etc. Alright? So let's have a look at this. Number 1. So you can think of, in this case, of multi-layered functions. Actually, we already did this when we reviewed composition function. Remember, we related to those nested adults, like having one and then another one inside, right? So this is pretty much what composition functions work like. You have an outermost function and then you have an innermost function, right? So the outermost function is going to be our f of x, and whatever inner function is going to be the g of x. And even if we have anything even more composite, so there's smaller functions and innermost functions, etc., etc. So let's identify those functions in this case. So in this case, we have the function f of x and g of x. So f of x is the outermost function. So what do we have inside of the radical? We have this x squared plus 1. That's the inner function. But what would be the outermost function in this case? The square root of x. So just the square root of x. And the innermost function is x squared plus 1. So if we do the composition f evaluated at g, so that's going to be the function f, which is the radical function evaluated at g of x. But what's g of x? We get back to the function h of x, right? So what are we doing? We're given the function, we are breaking up the composition in this case. All right? So the outermost, the radical, the innermost, the x squared plus 1. Let's look at the next example. E to the x squared plus 3x, f of x, something, g of x equals something. All right, what's the outermost function? So in this case, well, actually we can look at the innermost function, which is in this case, it's going to be the polynomial. Because the polynomial x squared plus 3x gets evaluated at the function e to the x. That is, f evaluated at g, that's the function e to the g of x, but in this case g of x is x squared plus 3x, which is in this case the given function. Alright? Again, what are we doing? We're breaking this apart. Alright? So we need to have an understanding of how composition functions are constructed and deconstructed, most importantly. Alright guys, so number one, so let's move to the calculus of composition functions. Well, so what if we want to find the derivative of f of x equals 1 plus x squared plus 2? And in this case, this is a composition function. This is some f of x equals x squared and g of x equals 1 plus x squared. So this 1 plus x squared gets plugged in here to obtain this 1 plus x squared quantity squared. Now, okay, to find the derivative of this function, number one, how about we write f of x equals to 1 plus x squared times 1 plus x squared. So that is the product of the quantity inside of the parentheses times itself. That's what the power 2 really means. If we had a 3, then we would multiply this 3 times. If we had a 4, we would multiply 4 times. But well, let's not get too crazy about it. So number one, let's FOIL. 1 times 1 equals 1. 1 times x squared, that's x squared. X squared times 1 and x squared times itself. Combine like terms. And find the derivative. And this one is really easy to do just using the general power rule. What's the derivative of 1? What's the derivative of 2x squared? What's the derivative of x to the 4th?
Wait, wasn't x squared plus x squared x to the power 4? So then it would be x to the power 8.
Oh, no, that's when we multiply. When we multiply the two bases, what do we do? Add the exponents. But when we have the same term, what we do is keep the same base and add the coefficient or subtract depending on the operation.
Okay.
So 0 plus 4x plus 4x cubed. Okay, so here's the thing. Okay, this one it's okay to do it without the chain rule. What if I had instead f of x equals 1 plus x squared to the 3rd power? Well, I think it's still doable to do the foiling 3 times, but I don't think that's the most efficient thing to do. What if we had instead to the 100th power? What about to the 2022nd power? And in fact, I will do that. But I'm not going to do that by foiling this 2022 times. Of course, we're going to use the chain rule in this case. Well, let's look at the definition for the chain rule. Hopefully we get the chance to do a couple of exercises. We'll see about this, all right? Okay, so if we have a function, a composite function that is differentiable, both are differentiable f and g, well, so we differentiate the outermost function, keep the inner layer intact, and multiply by the derivative of the function inside of the parentheses, all right? So, okay, let's do a couple of examples using the chain rule. Let's see. So what do we have? H of x equals to, actually let me do letter B first. I think I should have done B to be the first one and not H. Well, so all we have to do is identify the composition of the function. In this case, we have a composition of 2 functions. The function something cubed, that's the outermost function. And inside of the function something cubed, we have that binomial, which is 7x squared to the 7x squared plus 5. Are you guys following me so far?
Yes.
Okay, so what are we going to do? Let me put this back in. So we are going to differentiate. So something, so the 3 goes in the front, 3 times something to the 3 minus 1, which is 2. Keep the something inside. And then multiply by the derivative of the inner function. What's the derivative of the inner function? 14x. We're done. We're done with the calculus. Let's simplify this using our algebra. So 14 times 3, 12, that's 1. 42, so that's 42x times 7x squared plus 5. Final answer. Let me go back to the exercise we did before without the chain rule, by actually doing all the algebra. So in this case, let me use a different color here. So f equals 1 plus x squared f prime, so that should be 2 times to the first 1 plus x squared. What's the derivative of 1 plus x squared? Just 2x. Okay, so that's 2 times 2x, that's 4x times 1 plus x squared. Isn't it the same result? Factor 4x, that's 1 plus x squared. But which one is quicker, the chain rule or foiling?
Chain rule.
The chain rule. Alright, so we're going to do the chain rule. Let's do another example using the chain rule. Alright, let me go back to letter A. Okay, so for letter A, we cannot just differentiate the way it is because we need to have an exponent. And in this case, it doesn't look like an exponent function, but we can write this radical function as x squared plus 1 to the 1/2. And we're ready to find the derivative of this function. H prime, that's number 1, 1/2 to the 1/2 minus 1. What's 1/2 minus 1? Negative 1/2. Keep the inside intact. And now multiply by the derivative of the inside. What's the derivative of x squared plus 1? 2x. Well, there's a couple of things that we can do over here. Number 1, divide out these 2's and change this negative exponent into a positive exponent. That's going to leave us with x over x squared plus 1 to the 1/2, and in this case go back to radical notation. By the way, there's no way we could have differentiated the function without the chain rule, because unfortunately we cannot FOIL this with rational powers. We could have FOILed to the second, to the third, to your favorite power, but in this case, well, we're not for rational power. So let's do one more and then we call it a day. What about the derivative of the exponential? Okay, h prime of x. What's the derivative of the exponential? Remember how the derivative of the exponential is itself? The exponential e to the x squared plus 3x, and then well times the derivative in this case of the function that we have in the exponent. What's the derivative of x squared plus 3x? 2x plus 3. Well, let's just write this in the front, 2x plus 3 e to the x squared plus 3x, and we're done.